Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the how to solve or how to calculate lambda max by using unknown system, right? And number of different example we have solved based on Woodward and Fisher rule or by following Woodward and the Fisher rule. In this chapter there are two systems we have learned. One is a Dine system and another one is a unknown system. The values for base value for Dine system, as we know that only one base value is there, and which is a 215 nanometer, whereas in a unknown system, and as we know that unknown system, the unsaturated carbonyl compound are termed as a unknown system, and that unknown system has three different base values depending upon the Z, which is represented in a previous lecture. If Z means that group is a alkyl or the ring residue, or which is a 6-membered ring, then we can take the base value for unknown system similar to or identical to Dine system, which is 215 nanometer. If Z is a hydrogen atom, means that group becomes as a formyl group or the aldehyde group. If that aldehyde group in a conjugation, then that unknown system must possess the base value is a 207 nanometer. In some books it is given as a 210, but as far as the T.Y.B.Sc level is concerned, you must consider 207 nanometer, which is a fixed value for unknown system for the aldehyde. If there is a carbonyl group which is attached to the 5-membered ring, then the base value turned to be 202 nanometer. So while solving the problem based on unknown system, you must be very aware what type of the unsaturated carbonyl group is. So three different base values. Once you identify the correct base value, then rest of the thing is easy, and if you follow the short form which I have given, then there is no question of getting as a wrong answer. You definitely get the correct answer. So follow that rules. So today what we are going to see, the last point remaining in this chapter that we are going to discuss, we are going to cover in this lecture. So before starting this topic, that is the application of the UV spectroscopy, and as at the beginning I already told you that every spectroscopic method, the main application is to determine the structure of the unknown organic compound. So that is there. Let us discuss about some color and the visible spectrum. So in the broad spectrum of electromagnetic radiation, the visible light has a very small region, 400 nanometer to 800 nanometer. Human eye respond only in this region. Human eye respond only in this region whenever white light falls on a substance. It may be totally reflected and the substance appears white. On the contrary, if the molecule totally absorbs all the radiation, it appears black. However, if this molecule absorb a part of the radiation and if this molecule absorb a part of the radiation and reflect the remaining ones, it appears to be colored. For example, a molecule which absorbs radiation with wavelength 400 nanometer, which correspond to color blue, it will appear yellow to the human eye, which is complementary color to blue. The complementary color is also called as absorbed color. The complementary color are also called as absorbed color. And thus we observe the color complementary, that is absorbed, and hence blue and yellow colors are complementary to each other because the absorption of either of these two colors from the white light gives the other. So, like physical and chemical properties of organic compounds, there is a definite relationship between the color and constituents. For example, benzene is a colorless because it reflects all the visible light without absorption, but nitrobenzene is a pale yellow colored liquid and absorbed in the visible region, and this is because the NO2 group chromophore decreases the energy and shift absorption to longer wavelength. The color of organic compound is mainly due to the presence of chromophoric groups. The intensity of color increases with increase in the number of chromophores in a compound. And from the above example, we conclude that highly conjugated organic compounds are colored because they possess lambda max value in the visible region. Beta carotene, a natural pigment found in carrot and tomatoes has a lambda max 415 nanometer due to presence of 11 carbon-carbon double bond. And now the actual application of the UV spectroscopy. Number one, detection of structure. First one is a detection of structure. Detection of structure. So that is the first application of UV spectroscopy, which is detection of structure. UV spectroscopy is one of the method of studying structure of organic compound and may be useful in determining the presence or absence of chromophore. The steps involved in the structure determination are: number one, collect the information on the compound, determine what element and functional groups are present, perform quantitative tests, etc. Using Woodward and Fisher rule given earlier, calculate the possible lambda max for the expected chromophore and compare it with the experimental value obtained for unknown compound. Search for a model compound containing a similar chromophore, study its absorption characteristic and compare the spectrum of unknown with that of model compound. Then determination of stereochemistry, cis and trans. Second one, determination of stereochemistry. First one is a detection of structure. Second one, detection of stereochemistry. Detection of stereochemistry. Stereochemistry, which is a second application of UV spectroscopy. And as we know that generally this is a cis and trans, and you might be aware of cis and trans. Cis means similar group are on the same side of the carbon-carbon double bond is termed as a cis isomer, whereas trans isomer means what? Similar group or the identical groups are opposite to the carbon-carbon double bond are termed as trans isomer. And if this type of the isomers are present in the organic compound, we can easily identify by this method, which is UV method. A trans isomer usually has a greater lambda max and lambda max value than the corresponding cis isomer, and thus UV spectra is useful to distinguish between cis and trans isomer. Cis isomer absorbs at a lower wavelength than the trans isomer due to two reasons. Reason number one, in a cis isomer there is a steric hindrance. How? Let's see over here. Let us see one of the structure I am drawing here. this is a structure of one of the compound. You can identify easily like this. Here look at carbon-carbon double bond. This is the first essential criteria for cis isomer. This is a cis T.Y.B.Sc, we can call it as a T.Y.B.Sc, both the benzene ring. And here if you look at ortho position, there is a hydrogen atom. At ortho position there is a hydrogen atom, and there is a lot of physical interaction. They are pushing each other, and that type of the thing is called as a steric hindrance. Here is steric hindrance, and due to that steric hindrance, the internal energy, or what we can call it as a planarity, is lost that molecule, and therefore the absorption will be at the shorter wavelength or at a short wavelength. Let us see in another case where the two bulky groups are well separated from each other. There is no steric hindrance at all, and that's why. And also you can see, look at here, carbon-carbon double bond, single bond, double bond, single bond, double bond. The length of chromophore also goes on increasing, and hence the lambda max here, this is a trans T.Y.B.Sc. This will be the trans T.Y.B.Sc, and which has here lambda max is a 280 nanometer, whereas this trans T.Y.B.Sc shows as a lambda max 296 nanometer. And by observing this, by comparing these two values, we can clearly understood that how trans isomer absorb as longer wavelength, whereas the cis isomer absorb as shorter wavelength. And in a cis isomer there is a steric hindrance, as I already told you that trans isomer absorb at a longer wavelength than cis isomer due to two reasons. Reason number one, in a trans isomer the molecule is a planar and there is no steric hindrance. Number second, the length of chromophore increases. This situation demands pi to pi star excitation, hence less energetic, and hence absorption toward longer wavelength. These are the two reasons, and that's why the trans T.Y.B.Sc will be the showing lambda max or the band at higher peak. Now the last application, that is the third application of UV spectroscopy, will be this one. Let us see here, third application of UV spectroscopy, that is what is that? The strength of hydrogen bond. The strength of hydrogen bond. Strength of hydrogen bond. This is the third application of this UV spectroscopy. The strength of hydrogen bond can be calculated by running the UV spectrum in different solvents like water polar and N-hexane non-polar. Consider UV spectrum of acetone. Let us see here CH3 C double bond O, CH3, which is a structure of acetone, and when it is here N2 pi star transition non-bonding to anti-bonding pi star, when it is dissolving or this spectra is run in non-polar solvent N-hexane, and then the lambda max appears to be 297 nanometer, and where it gives 121 kilocalorie per mole. This much amount of energy is generated over there, and if you find here in a polar solvent N2 pi star transition once again, but here the solvent is a water, it is a polar solvent as we know that, and it is a non-polar solvent. N2 pi star transition, and it is found to be 264.5 nanometer. This is and where the value is comes around 126 kilocalorie per mole. And now from that we can easily calculate the strength of hydrogen bond. The strength of hydrogen bond is found to be, if you 126 minus 121, it comes around 5 kilocalorie per mole, and this is the strength of hydrogen bond. We can calculate in this way. Water forms hydrogen bonds with carbonyl carbon of acetone, whereas in N-hexane no such hydrogen bonding, and the difference in the lambda max values in water and in acetone should directly give the strength of the hydrogen bonds. So in this way we have seen there are three applications of the UV spectroscopy here. So in this way we have covered all the point whichever essential for as far as exam point of view is concerned. Let me give some more probable question, what type of the nature of question may appear in the exam. For 1 mark question is generally explain N2 pi transition with suitable example, or explain the term axochrome with a suitable example. Axochrome, everybody knows that it is a isolated functional group. It is a functional group. It is not absorb UV radiation, but when it attached to the chromophore, the length of lambda max it goes on increasing, so that type of the thing is called as axochromes. Then maybe explain the following terms with a suitable example, like as a red shift, bathochromic shift, blue shift or apochromic shift, chromophores. Explain pi to pi transition with a suitable example, or define hyperchronic and hypochronic shift in spectroscopy. Then cis-stilbene lambda max 280 nanometer, trans-stilbene lambda max 296 nanometer. Why? Just now we have seen a reason. Then trans-stilbene absorb at higher wavelength than its cis isomer. Question mark, why? Or aniline shows hypochronic shift in acidic medium. That also we have seen with the help of example. Then write the application of UV spectroscopy in organic chemistry. You just mention at least 2 applications, you will get 1 mark. And then distinguish the following pair by UV spectroscopy, and they will give some structure, so you can identify that very easily by using as a UV spectroscopy. That also we have explained. Then calculate the lambda max value for following compound. There are 2 systems, as we already know that one is a enone system and another one is a dyne system. So by knowing that system, we can easily find out those lambda max with the help of, because the values no need to remember, they are given at the end of that question paper. So there are 3 tables are provided, in that we can choose. I think with this, let us stop today here. Remaining we will see next time, that is chapter number 6, infrared spectroscopy, and how infrared spectroscopy will be helpful or the useful for the structure determination. So that we will see tomorrow. Let us stop today here. Thank you. Have a nice day.